talk about, the main result we're going to talk about in the first part of the course is Rasboroff's result about monotone circuit complexity, but I think I want to provide a bit of motivation for that by saying in some detail what P and NP are, and a little bit about the Klieg problem, which is what Rasboroff's result concerns. So, roughly, I'll give some examples. P is things that you can compute in polynomial time. NP is things that you can check in polynomial time. And NP complete is something that is in NP and has the property that any other problem in NP can be reduced to that problem. So I want to say in much more detail what I mean by these words. So let's start with the easy one. P. So if you want to be formal about it, which I won't be, you can say something like a Boolean function f from 0,1 to the n to 0,1 is computable in time m if there's a Turing machine that after n steps outputs whatever f output should be, something like that. But we don't want to get too hung up on details because one of the great things about the notion of polynomial time computability is it's very robust, as I commented last time. You could, if you wanted to, just say it's anything I can program my laptop to do in polynomial time, or in a sort of polynomial number of steps. Whatever you mean by step, and if somebody else means something different, then it still will be the case under any reasonable notion of step that f is computable in polynomial time with this definition, if and only if it's computable in polynomial time with this definition. And what I showed last time was that if something is computable in polynomial time, then there is a polynomial sized circuit. Or for each n, there is a circuit of size polynomial in n that computes it for every input of size n. But let's just give a couple of examples of problems that can be solved in polynomial time. So one would be a classic one. We've got a graph G, n vertices, and you have two vertices, x and y, and the question is, what is distance between x and y, where the distance is defined as the length of the shortest path in the graph. So let me just, I'm not going to write formally what an algorithm for doing it, but let me just convince you that there is an algorithm. Here's what you do. You look at x, and all the neighbours of x you label with a 1. And all the neighbours of those you label with a 2, except that x will be a neighbour of those, and that's already been labelled with a 0, so you don't label that with anything at all. So all the neighbours of these you label with a 2, and you just keep going, and at some point you'll hit y, and whatever you've labelled y with is the distance. And that takes polynomial time. If you really want to convince yourself that it takes polynomial time, what you could do is, at each stage, this is not a very good way of doing it, at each stage of the process you could just run through all the vertices, check whether there's a labelled vertex next to your vertex, and your vertex is not labelled. If so, label it n plus 1, where the existing label was n. So not n, k or something. So there's a sketch of a polynomial time algorithm for that. And here's another one. Is the tripartite. And that's very similar. What you do there is you do exactly the same thing, except that you do it mod 2. So all the neighbours of these are now, if I start with a naught here, then I'll label all these ones naught again. And that way I build up an entire labelling, and then I go through and check, have I ever got a naught that's next to a naught? And if I have, then there'll be an odd cycle in the graph, and it can't be bipartite. And if I haven't, then I've got a sort of consistent, well, it gives me a two colouring of the graph with noughts and ones, and that proves that it's bipartite. I'm assuming it's connected there, actually, but otherwise you just do it component by component. So there are a couple of polynomial time algorithms. One thing I want to draw attention to is a difference between these two questions. So one was sort of calculate something, and the other was a question with a yes-no answer. So the second type of thing is called a decision problem, and from a theoretical point of view, it's convenient to focus on decision problems because they can be modelled in a very simple way, just a Boolean function from 0, 1 to the n to 0, 1. And you can focus on those because you can sort of prove in silly ways that if you can solve all decision problems, then you can solve sort of more like calculation problems. I'll come back to this point, but for this, what is the difference between x and y? You could ask, is the last digit in binary of the distance between x and y a naught? And keep going like that, and if you can answer all those questions, then you calculate the distance. Those sorts of judges come up all over the place in this sort of business. They just give you the option of making things simpler. Okay, so P, I don't need to say much more about P because it's, if I just say computable in polynomial time, that's a pretty intuitive concept. I suppose I didn't really say that this only took polynomial many steps, but it's easy to see as it does. So what about NP? Well, I will start with an informal definition and then give a slightly more formal definition, which is a rare example, I think, of where the formal definition really does clarify things in a useful way. Often, the informal definition is what you really care about, and formalizing it is just to sort of reassure yourself that it can be done. In this case, I feel that the formal definition very much helps to understand the informal one. So I will start by sort of saying problem where the answer is checkable in polynomial time. I've got a couple of examples, then I will go on and say a bit more about what it means formally to say checkable in polynomial time. So the first one, so G is a graph with n vertices, m less than n. Does G contain a G of size m? In other words, does G contain m vertices, any two of which are joined together? That's what a cube means. Now, why is this in NP? This, by the way, is nobody knows a polynomial time algorithm for solving this problem. And if you did, you'd have proved that P equals NP and surprised the world big time. But it's trivial that it's in NP because here's how to check. If somebody says, here's a clique of size m, this vertex, this vertex, this vertex, then all you have to do is look at each pair of vertices that have been nominated by this person, see whether they're joined, and that can be done in time, or sort of m choose 2 steps or something. So it's a completely trivial thing to do. So checking that somebody's answer is correct, if they give you the information of what the clique is. So if somebody just comes along and says, yes, then checking that in polynomial time is not so easy. But if somebody says, yes, and here's my demonstration that it's the case, and gives you a subset of the vertices, then it's easy to check. So that's the thing that makes it in NP. Another example, so that's a decision problem. That's a famous example of an NP problem that is not a decision problem, but can be sort of stupidly converted into one. So n is a product of 2 primes. What are they? So this is what would be called a search problem. We're searching for the factorization of n. Again, it's in NP because if somebody says P and Q, then in polynomial time you can multiply P and Q together and get n. And by the way, I should say, this is a little remark that one always has to make. In this case, polynomial time is not polynomial in n. Trivially in time polynomial in n, you can find a factorization just by checking everything by brute force. But it's polynomial in the size of the input. And what is the size of the input? It's the binary. What is the input? It's the binary expansion of n or something like that, which has size log n. So when you talk about this, you're looking for an algorithm that will be polynomial in the number of digits of n rather than the number n itself. But that remark aside, this would be a search problem that's in NP, because if I give you the two primes, you just have to multiply them together, and that can be done in time polynomial in a number of digits. So you could convert this into a decision problem by saying something like n is a product of two primes. Does the smaller of those two primes have final digit 1 in binary expansion? Does it have penultimate digit 0, etc., etc.? And that way, if you can answer all those questions, if you've got a black box that will solve all those decision problems for you, you've solved this problem. And are each of those decision problems in NP? Yes, because again, you can just present the primes P and Q, check that they multiply together to give you what you want, and check that they do have the specified digit in the right place. So you can if you're just sort of thinking theoretically about NP complete problems, it's enough to restrict attention to decision problems. So those two are very easily seen to be in NP. Here's one that's in NP. Rather less trivially, and I'll sketch why this is in. You're given a positive integer n, and you're asked, is it a prime? Now, if I ask you, is it composite, that's obviously an NP, because you just exhibit two non-trivial factors, and then somebody can check whether they do multiply to give you your n. But it's not quite so obvious if you've got a number n, whether there's some polynomial way of checking whether it's prime. Unless, of course, you've heard on the news that being prime is something that can be computed in polynomial time. But that's not trivial. Although it's easier than people expected. But I can I can convince you very quickly that it's in NP, and that's not sort of totally obvious either. Even just having a polynomial, so what you're allowed to do to prove that it's in NP is you're just allowed to write down some stuff, and in polynomial time I can use that stuff to convince myself that it's prime. Can you convince me in polynomial time that n is prime? That's the question we're asking. You're allowed to draw as many rabbits out of hats as you like, but it must only take polynomial time. So here's a small observation that drives the proof, and drives a lot of interesting stuff in computational number theory. That n is going to be prime if and only if you look at the multiplicative group z over nz, well, if n is prime, that's known to be cyclic. And what's more, it's got order n minus 1, so there must be some number a mod n that has order n minus 1 in the multiplicative group mod n. So let's just write that. N is prime. I'll justify the if and only if in a moment. If and only if there exists a such that a to the n minus 1 is congruent to 1, and a to the m is not congruent to 1, then m is less than, or 1 less than m less than n minus 1, and all that is mod n. So if n is prime, that follows from the result in number theory that the multiplicative group is cyclic. If n is composite, well, at least we know that the integers mod n form a group, and that group has order strictly less than n minus 1 in that case, and the order of every element divides the order of the group, so this can't be the case if n is composite. So we have a sort of... So what this suggests is, in order to convince me that n is prime, all you need to do is exhibit a generator and show that it's got, well, just exhibit an element and show that it has order n minus 1. So if you can give me an A, and a proof that A has order n minus 1, then you're done. So so exhibiting A, just do it. Of course, that's not an easy thing to do, but I think if you leave a generalized Riemann hypothesis, then you can just try 1, 2, 3 all the way up to log n squared or something, and then you'll be okay. So, anyhow, so that could, in theory, be done in polynomial time. That's a famous thing. Either you can do it in polynomial time, or you leap to world fame because you've disproved the generalized Riemann hypothesis. Anyway, so exhibit A. But actually, how do you prove that the order of A really is n minus 1? Well, there are two steps. One is the easy step. Just multiply it, raise it to the power n minus 1. Just a small thing to work out there. You have to be a little bit clever about raising to the power n minus 1. You can't just say, let's work out a squared, a cubed, a to the fourth, and so on. So what you do is you work out a squared, a to the fourth, a to the 8, a to the 16, a to the 32, and then pick an appropriate subset of those and multiply them together. So it can be done in polynomial time in the number of digits of n rather than n itself. But you've also got to show that a to the m does not equal 1 for any factor of n minus 1. And in order to do that, it kind of helps to have the prime factorization of n minus 1 at your disposal. So you just draw out of the hat n minus 1 equals p1, p2 up to pk. We need to check that those multiply to give n minus 1. Can be done in polynomial time. We also need to check that all of those are prime. But by induction, we know how to check that they're all polynomial, they're all prime in polynomial time. And again, you have to be a little bit careful, but the number of digits of these things is sort of quite a lot smaller than the number of digits of n, and you can check that this really does work, that it doesn't all sort of blow up massively. And it gives, that's all I'm going to give in this case. It's not very hard, I've given you enough, it's a little exercise just to check that this recursion does actually work and gives you something that gives a polynomial time check. So that's a sort of non-trivial example of something in NP. So now let's go a little bit more formal about what NP is. So supposing I've got a Boolean function from 0,1 to the n to 0,1. When do I say it's in NP? If there exists another Boolean function.
So, you've got to check all divisors of n minus 1.
Sorry, how do you mean?
You've got to, for every divisor of n minus 1, you need to check that a to the n is not congruent to 1.
Yes, but you can do that by... Wait a minute.
And there might be more than log n to any parameter.
You just need to check n minus 1 from pi for each other.
Yeah.
Yes, I think you just have to check the biggest ones in each direction, so to speak. I think it's...
Okay, yeah, I believe that. Yeah.
So, yeah. That's right. As long as it works for n minus 1 over pi for each I, then all other divisors will divide one of those. And all other proper divisors will divide at least one of those.
You also need to check that every pi is prime.
Yes, so that's the bit you do recursively. So each pi will be provably prime with enough rabbits out of hats by induction in time polynomial number of digits of that pi. The sort of sums of the number of digits of these pi's is roughly n, and you can check that that makes them small enough that this recursion actually does lead to a polynomial time check. I haven't absolutely demonstrated that, but I'm asking you to believe that. And it's not very hard. If you're curious, I recommend it actually. It's quite fun to check that. So going back to this, if function f is in NP, if you can find a function g, another Boolean function, where I'll think of, such that g belongs to p, And also this number m, this mysterious number m, is bounded by some polynomial in n. So m is not too much bigger than n, and g is a polynomial time computable function 0, 1 to the n plus m, with the property that fx equals 1 if and only if there exists a y such that gxy equals 1. So here x belongs to 0, 1 to the n, and y belongs to 0, 1 to the n plus n. Let me just now try to explain this more formal definition by showing how it works in the case of a clique, graph containing a clique. So in the case of the clique problem, we will take a graph with n vertices. So this n will become n choose 2, and x, the given graph, will be a set of noughts and ones corresponding to which edges belong to the graph and which edges don't belong to the graph. So you're given a sequence of n choose 2 noughts and ones, and you're asked, does the corresponding graph contain a clique, or more in this language, we've got a Boolean function that will give you 1 if the graph contains a clique, 0 if the graph doesn't contain a clique, of size. Sorry, I've got a letter m here. Let's say we're looking for cliques of size s or something like that, just not m, which I had over there. So what should we choose as our m? We'll choose as m. So n, instead I'm taking n choose 2, and m I'm taking as n in this particular instance. So now I've got, what will g be? G will be the function that does the following. You input a sequence of length n choose 2, which represents a graph with n vertices, and it tells you which edges are in and which edges aren't in. And then another sequence that represents a subset of the vertex set. You just put a naught when you're putting that element not in your subset, and a 1 if the corresponding element is in your subset. And what does G do? G just looks at the graph and the subset of the vertex set and determines, well, two things: whether the subset of the vertex set really does have size S, and two, whether any two vertices here, so say 2, 3, you look back to here to see which of these n choose 2 things corresponded to the pair of vertices 2, 3, and see if you've got a 1 there. And if you've got a 1 in all the situations where you should have a 1, then G will output 1. So you can see that what I'm doing with this is more or less exactly what I was saying when I had the check thing. So going back to the non-Boolean functional way of looking at it, you could say that the reason the clique problem is in NP, so the clique problem is asking a question about graphs. I can ask a question about something slightly bigger, a pair, graph, subset of vertex set, ask a trivial question about that, and then the original question I asked about graphs has answer yes, if and only if there exists something over here such that the trivial question about the pair has answer yes. So the question, does the graph contain a clique, has answer yes, if and only if there is a subset of the vertex set such that the question, is this subset a clique, has answer what? Has answer yes. So basically, well, we can look at this in a slightly geometrical way. I'll draw two axes. One is 0, 1 to the n, and the other is 0, 1 to the m. We can identify a Boolean function with a set of places where it takes value 1. So that will be some subset like this of 0, 1 to the n cross 0, 1 to the m. And what is the Boolean function f if it's in NP? So if this is representing the Boolean function g, the Boolean function f is the projection of this function, or it's the set corresponding to the Boolean function f is the projection of the set that corresponds to G down onto the 0, 1 to the n axis. So what I'm saying here, in this sort of way of looking at things, I'm saying that the set of things where you get value 1 for f is a set of places where there exists something up here that has value 1. So in terms of, because last time you may remember when I talked about circuit complexity, I also formulated things in terms not of functions but of sets. I looked at the set of places where looking took value 1 and argued that sets corresponding to functions with low circuit complexity are sets that you can build up in a small number of steps using unions, intersections, and complements. So NP is introducing one extra operation into the picture, namely projection. You take 0, 1 to the n, cross 0, 1 to the n, take your set and you just project it in an obvious way onto 0, 1 to the n. And in a sense, the big question in theoretical computer science is projection giving you much more than you had before? And it sort of feels as though it is. But that's the thing that people can't prove. So we've done P and NP. Now I want to talk about NP complete. So I'm going to go back to being a little bit informal. So the problem is, maybe I'll say, the problem is NP complete. If it's in NP and any other problem, any problem, let's call it a problem, pi or something, any problem in NP can be reduced to pi in polynomial time. So roughly speaking, it's NP complete if given any other NP problem and given an algorithm that works in polynomial time for solving pi, I can convert that into an algorithm that solves the other problem in polynomial time. Now, it's far from obvious initially that there is such a thing as an NP complete problem. It's just a theorem that they exist. Though, well, two things. One is actually, once you see, I'm going to give you a sort of slightly trivial example in a way of an NP complete problem. So I think after that it's sort of obvious that they did exist after all. You see what I mean? But the other thing which you may well know about NP complete problems is that there's an awful lot of them. So the vast majority of natural NP things that you write down turn out to be NP complete. Things like the Cleek problem, that's certainly NP complete. Though I must say, since I happen to have given one of the important exceptions, which is the factorization problem. If you've got nobody knows. It seems incredibly unlikely that the problem of factorizing a large product of two primes is NP complete, but that's a somehow rather untypical problem. So here is my sort of semi-trivial example of an NP complete problem. It's nothing like Cleek, it's just I give you a circuit, so 10 inputs, it's not too big. Can we choose the inputs to give output 1? Why roughly is that NP complete? I mean, I'll be a little bit less rough in a moment, but let me just say, if you buy what I said last time, that any Turing computable function that can do its job in polynomial time can be converted into a circuit that does the same job with polynomially many gates, then take your problem that's in NP, take the function g that does the checking, devise a circuit that does the checking. A few of the inputs of that circuit correspond to the problem that you're really interested in, and the other ones correspond to the check. Fix the input of the problem, collapse the circuit in a certain way, and then you're asking, can you find a check that works? Let me just write something down to make that clear. I mean, I can see at least one person agrees with me that it's essentially trivial, but let's just write a little bit down. So I've got to take an arbitrary problem, so sort of sketch proof. That belongs to NP. So because it belongs to NP, I know that I can find G I keep overusing M. Perhaps I could just say of size N. No, better not. Size S or something. So 0 plus 1 to the N plus M to 0, 1 such that fx equals 1 then exists y with g xy equals 1. So that I can do by the definition of NP. Now, polynomial size circuit that computes G. So let's just draw a picture of what we've got now. You can make this even more trivial. I'm going to do a sort of collapsing operation, but it's actually completely unnecessary for the proof that there exists a problem that's NP complete, because I could even, well, I'll make this wrong in just a moment. So I've got a circuit that looks like this. N inputs here. And then M inputs here. The function I'm really interested in is f, which is just a function of these N inputs. The function I know how to compute is g, which is a function of all of these, and I know that f will give me 1 for some particular set of inputs, if only if I can find a whole bunch of further inputs, such that when I compute g, I get 1. So now let's just see how I can use my polynomial sized solution to the circuit problem. What I'll do is I'll just draw the circuit that computes G. Whatever. Let's imagine it was, say, the clique problem. So over here I might, I would stick in, I've got a graph and I want to know in polynomial time whether the graph's got a clique. I've got my magic algorithm that can decide whether circuits have inputs that give output 1. So I encode the graph here as a sequence of noughts and ones in an obvious way. And then, if I want to make this a circuit with m inputs rather than what I've got here, which is n inputs that I've chosen and m inputs that I'm allowed to choose, then you can do things like this. Supposing I'd chosen a naught and a 1, and this was an AND gate, then that would, I could just forget that naught and 1. This vertex here is forced to be a naught, and that sort of feeds through until I get rid of all the sort of fixed parts of the circuit. So for example, supposing I had a naught here, and an input that I haven't yet chosen over here, and this was an OR gate. Let's just do another example. what do I get here? I just get whatever I had up here, because naught or something is that something. So just by sort of collapsing things down, you can create very quickly a circuit over here with the property that there exists an input that gives you 1, if and only if there exists an input extending the encoding of the graph to get you a 1 for the function g, if and only if g has a clique in it. And you can do the same game for any NP function. If I want to compute the function little f, I stick in the values that I want to compute f for, and then collapse the circuit, and then I can find some inputs, some m inputs here that will give me 1, if and only if I could find m inputs such that for this whole thing I got 1. But all this collapsing is unnecessary. If instead I choose as my problem, I am given a circuit, I fix some of the inputs, can I then choose the rest of the inputs to give me an answer 1? Then the problem, then it really is sort of trivial in NP. Modulo the result that every Turing computable function can be produced by a circuit of comparable complexity.
Can we generate this circuit in polynomial time?
Yes. If you're given your algorithm, maybe that is it's not a totally trivial step, but I mean, you'd have to look at how I described the way we produce a circuit and convince yourself that what I told you to do there is something that can be done in polynomial time.
You could also just force the inputs to 0 and 1 by having a dummy input, and then A and not A will be forced to 0, and not A and not A will be forced to 1, just by sticking little extra bits on. Rather than stripping out bits of the circuit.
Oh, I see what you mean. I see what you mean. Yes, yes, yes. That's probably nice. So I just say that it is possible, given the specification of the Turing machine in polynomial time. It's not very nice, but it's possible to just look carefully at the proof that you can get a circuit and show how to produce that circuit in polynomial time. It's not just a pure existence argument. Let me now give 2 more examples of NP-complete problems. One is sort of fairly trivial from this circuit one, and the other... So one is going to be something one of the most famous basic examples of something called 3-SAT. And then once I've shown you 3-SAT, I will show you that the problem of finding a clique in a graph is also NP-complete. If you can always decide whether a graph has a clique of size n, then you can solve all NP problems. It's bizarre in a way that you could factorize large integers just because you can find cliques in graphs, but it really is the case that if you can do one, you can do the other. Well, that might be the case that actually doing that, if you try to implement that, if you sort of assume that someone's got a black box that finds you cliques in graphs, that it would be hard to do it in such a way that polynomial wasn't a rather boringly high degree or something like that. I don't know. So what about 3-SAT? So let me describe that. I thought I was going to get away without giving you various official names for things, but I think I'm going to. So supposing you've got some variables, x1 up to xn. A literal is something in the form xi or not xi. A clause is something of the form u1 or uk, where each of these are literals. maybe definitive definition allows ands, but I'm only going to be looking at clauses of this particular form. And a formula in conjunctive normal form is a big conjunction of clauses. So it's let's have an example. Say x1 or x2 or not x3 and not x1 or x2 or x4 or not x6 or x5 or something like that. That would be an example of a formula in conjunctive normal form. Incidentally, a formula full stop is just anything that you can build up out of xi's and not xi's using, well, actually there are two equivalent definitions, but anyway, let's use using ands and ors. Or I could have said anything you build up out of the xi's using ands, ors, and nots. It's not an equivalent definition because we could do different class of things, but they calculate the same sets of functions. You can convert a formula that uses nots anywhere into one that just uses nots at the top. For example, I've got a knot here, I can bring it inside and use De Morgan's laws to change ors to ands and that sort of thing. And a formula is closely related to a circuit. What it is you can represent a formula as, let me try doing it with this one. So I have x1, x2, x3, and I'll not make it binary, so I'll allow myself unbounded fan-in OR gate. And then I've got not x1, x2, x4, and not x6. Now you may ask why I'm doing it like this. Why didn't I have an x1 and then a not gate and that sort of thing? I'll talk about it in just a sec. And an x5 over here. And here I've got an AND bit. A formula, the size of a formula is measured by just how many of these xi's you had to write down to write the formula. And that corresponds to a circuit that takes the form of a tree, with the one exception that you're allowed to repeat inputs. So I'm allowed to insist that this input is the opposite of this input, that kind of thing. So there's another notion. It's a formula, the set of functions that you can compute using a formula of size m is much smaller than the number of functions that you can compute using a circuit of size m, because basically formulas are like circuits, but they're forced to be trees. However, it's not known, this is one of the great open problems, it's not even known whether there is a problem in NP that can't be computed by a formula of polynomial size. So about circuits, formula, when you play around with them, you sort of feel, well, they're so much more restricted than circuits, that at least that question must be answerable, but it turns out that even that one's not answerable, or nobody knows how to answer it. Anyway, we're not going to talk too much about that. Let's just go back to a formula in conjunctive normal form. A formula is satisfiable if the obvious thing holds. You can just choose values for the inputs. It gives you 1. So up here, this one I'm sure will be satisfied because I haven't written enough constraints. So I could choose x1, just make sure that x1 is 1, x2 is 1, and x5 is 1, and there's no problem at all making that one. So that was obviously satisfiable. So 3-sat is the following problem. Given a formula of size n such that each clause, as I say, a CNF formula, was that each clause has size of 3. Answer the question, is it satisfied? I haven't said this, I should have mentioned this a little earlier. The word problem is traditionally used to mean class of problems. So, the problem is not just a single question with a yes/no answer, it's a question, it's a question where you've got some variable input, and whatever it is, you don't have to answer the question yes or no. So this is a problem, but it's really a class problem. Yeah. So why is 3-sat NP complete? Well, I'm not going to prove that from scratch. I'm just going to deduce it from the fact that the circuit question was NP complete. So what I have to do here, and this is typical of NP completeness proofs, I just have to sort of come up with some formula that forces you to do what a given circuit does. So let's just have a look at a particular gate. Supposing I've got input x1. So what I will do is that the inputs to the circuit will be x1, x2, x3 up to xn, will be represented by x1 up to xn. But then I'm going to have some more a bit like the straight line model of computation, that later further vertices of the circuit will be represented by further literals like xn plus 1, xn plus 2, and so on. Now what do I want to do? I want to devise a conjunctive normal formula of size n with each clause having size at most 3 in such a way that if, say, this was an AND gate, then xn plus 1, in order for the formula to be satisfied, would absolutely have to be x1 and x2. So let's just see how to do that. So I'm going to construct, given the circuit, I shall construct a whole lot of things that are going to. I'll have a variable for each vertex of the circuit, and I'm going to construct a formula that will force any satisfaction of that formula essentially to do the same computation that the circuit does. So what if I've got an AND gate here? What must I not do? I mustn't have, for example, 0 here, 0 here, and 1 here. And I mustn't have 0 here, 1 here, and 1 here. And I mustn't have 1 here, 0 here, and 1 here. And I mustn't have 1 here, 1 here, and 0 here. So let's just do the first one. If I'm going to avoid having 0, 0, 1, then I must have either x1 or x2 or not xn plus 1. So that's just ensuring that I won't stupidly put a 0 here, a 0 here, and 1 here. And then I've also got to ensure that I either have a 1 here, or a 0 here, or a 1 there. So I have to think about this rather carefully. I mustn't have 0, 1, and 1. So that must be a not xn plus 1. Now I think I can do it on auto. So I've got to go through the other. And because it's an AND gate, sort of 3 of them are going to do one thing and the fourth one will do the other, so this must be AND not x1 or not x2 or xn plus 1. So this last one ensures that you don't have x1 and x2 but not xn plus 1. So any formula, so the point is that any formula that satisfies all these clauses must have the property that the value you choose for xn plus 1 is the AND of the values that you chose for x1 and x2. And you do the same for OR gates and the same for NOT gates, and you build up a formula that way. And that has the property then that any way you choose the variables. Finally, of course, mustn't forget the good old output, xn. We want that output to equal 1. So we also have to have xn on the end of our 3-sat formula. So now, what have we done by all this? We've achieved that any formula that satisfies any sort of way of choosing the variables to satisfy this formula will have the property that the corresponding, if you look at the corresponding values in the circuit, the values taken by the variable will be computing the circuit. Because of this xm that we've tacked onto the end, the output will have to be a 1. And so this formula is satisfiable if and only if, well, what have we got to choose when we do this formula? Once we've chosen x1 up to xn, all the other ones are determined, because that's how we devised the formula. Once we've chosen x1 and x2, that determined xn plus 1, and we just go through. So all we've got to choose is x1 up to xn. Therefore, this formula is satisfiable if and only if there's a way of choosing x1 up to xn such that xn comes out as a 1, such that in other words, such that this circuit actually computes. And gives a 1 for the corresponding zeros and ones as inputs to the circuit. So that means that if we can have a polynomial time algorithm that looks at a formula like this, we've managed to solve the circuit problem, and then because we managed to solve the circuit problem, we can encode any algorithm into a solution of a sat like this. So I've run out of time, so next time, it won't take me very long, I'll just give a quick sketch of how to get cliques in graph, which is slightly less obvious, but not, it's definitely an exercise rather than a serious theorem, so it's a fun thing to think about again. And once I've done that, I really will make a start of Razborov's proof that the problem is hard to do with monotone circuits.